Hello everyone, welcome back in the course of higher surveying, and we are in module 4, error, accuracy and adjustments computation. In last two lectures we have learned many things. In first lecture we have differentiated between the precision and accuracy. We have seen the example of triangle and how to find out the accuracy of each angle or accuracy of the complete triangular system. Also, we saw that precision is indicated by standard deviation. So, let us say if I take n number of observations for angle alpha and if I find out the mean and standard deviation. So, standard deviation of sample will represent the precision value, but it is not an accuracy. That is what we have learned. Okay, then we talked about the triangle example. We have find out the adjusted values. That means using a condition equation, we put the observations alpha, beta and gamma, mean values of those three variables, and then we try to put the condition that sum of the three angles in a plane triangle should be equal to 180 degree. And using that 180 degree reference value or the true value, we have find out the what should be the accuracy of triangle system, or if E is the accuracy of the triangle system and we are measuring all three angles equally, then E by 3 will be the accuracy of each angle. That is what we have done in the first lecture. In the second lecture, we have learned how to use the law of error propagation to find out the precision in the dependent variables. Now, let us look again in the triangle example, and as we said that it is a kind of adjustment process. So, today we are going to talk about the adjustment process in detail. Right. We are going to use law of error propagation also to find out the quality of parameters, quality of variables and so on. Let us go into the third lecture of this module, which is observation equation method of adjustments. Books are here. You might have done the adjustments many a times. When you go into a bus and if there are 2 seats and you are 3 friends, you try to adjust there. Okay, but when we talk about the adjustments and computations in higher surveying, what does it mean? Let me recall a simple example. After the high school, when we were in 11th standard, we conduct an experiment in physics, and the experiment is the Newton's law of cooling, and accordingly we write that dt by dt is proportional to dt, or we can say T minus Ta. What's the meaning here? That rate of change of temperature is proportional to the difference of the temperature with respect to ambient temperature. What is my ambient temperature? It is temperature of the surrounding or atmosphere. T is the temperature of the material from which radiation is occurring and the heat is dissipated or energy is dissipated, while this is the rate of temperature change of the body. It is first order differential equation. If I solve this equation analytically, I will get T minus Ta equals to T minus Ta into e to the power minus kt. Okay, you are well aware of this equation. So, I know that there is some exponential curve is possible between the delta t and time t, as it is evident from this equation. And if you remember the experiment, we have drawn the curve also in x and y axis. Here my x axis, which is nothing but time. So, I mark time here, let us say t1, t2 and so on, let us say tn. Okay. On the y axis, we have delta t or dt, fine, and then we got this kind of data like this. But when we look into the data and if I try to fit or try to find out a curve, it is very difficult for me to fit or to find a single curve. I approached my physics teacher. I asked what could be a solution here? How can I put a curve through these points? It is very difficult. It is impossible for me, because if I add curve like this, can I fit this kind of curve? Because these are the points here, and through which if I fit a curve, it should be like this. But as I know that ideal curve should be like this, because it is theoretically proven and I am conducting an experiment. Okay. So, my physics teacher told me the real key here. he asked me to fit a curve through this data such that the curve should be closest to most of the points, or in other words I can say curve should be in a position such that it should have minimum deviation from most of the points or all of the points. Then I tried to do a lot of manipulation, and finally I could find a curve. The curve was looking like this. So this was the curve, I got it. If I draw the curve between t minus ta on the x-axis and delta t by d delta t, I got the data something like this. This was the data, and if I fit a curve, then it should be straight line. And again principle is same, that the curve should pass through maximum number of points, or the deviation of the points from the curve should be minimum. So we have done adjustment process or the curve fitting problem years back, and many a times we have done this thing in our laboratory experiments whenever we get some situation like this. So today we will do this mathematically, and then we will connect this process of curve fitting or maybe the line fitting to our adjustment computations, what we are learning in the module. Okay, let us go ahead. Let us take the simple example of line fitting. I have x data here, y data here. Let's say data is like this. I can see a linear pattern. I fit a line through this, let us say this line. Let us calculate the deviation from any point I. What is the meaning here? So this is xi and corresponding point is yi. But the point which is lying on the line, I call it yi hat. So equation of line is yi hat is equal to mxi plus c. I observed yi, this is observed data, and xi is also observed data. So if I make the combination here, this is pair xi yi, and this yi hat is simulated data. Now can I find out this deviation? I call this deviation as Vi. It is a deviation of the observed and the simulated data. So I write Vi equals to yi minus yi hat here, or I can also write it yi, which is observed data, minus mxi plus c, and like this. I can write it this way. You can see for this point, this term will be negative, and for this point it will be positive, right? So I want to take care of both the things, and as a result I'll make the square of this term Vi square, which is nothing but yi minus mxi plus c whole square, and then I make the summation for all the points. That means it is the summation of the squares of the error for all the points. Let us say if I observe n number of points, so I create this function phi. Well, now if you remember, in case of classical surveying or the basic surveying course, using a least squares principle, we have find out what are the possible values of m and c by these two equations, 1 and 2. We are going to implement the same thing here, but in a slightly different manner. Why? Because in higher surveying I have enormous data, not like 1 point, 2 points, thousands of points, millions of points, and so I need to use computers, and for that I need slight tweaking of the method, keeping the essence of the method same. What is the method which is compatible with computers and which is very easy to implement? Okay, so we have this equation. Let us say yi equals to mxi plus c, and where we said it's yi hat. That is very clear to us now. So let us write these equations one by one. So what's the meaning here? This is simulated one, And if I observe yi and if I add vi error, that is residual, then I will get yi hat, or yi plus vi, I can write mxi plus c. Remember, these are my observed data, and these are my unknowns that I want to find out for finding out the equation of line. So, if I write for n number of data, I will get this one, and so on. If I write for n number of points, I will get this. Remember, m and c are constant for a given line. So, let me write these matrices as V1 equals to mx1 plus c minus y1, V2 equals to mx2 plus c minus y2, and so on. So, Vn equals to mxn plus c minus yn. Okay. I am writing in the matrix form. And slight tweaking I am doing here, x1 1, x2 1, xn 1, and here I am writing m and c minus y1, y2, yn. So, I have written these n number of equations in the matrix form here. So, this matrix I call V matrix, this matrix I call A matrix, this matrix is capital X matrix, and this matrix I call L matrix. So, if I write the size of these matrices, it is n by 1 matrix, it is n into 2 matrix, X is 2 into 1 matrix, and L n into 1 matrix. So, these are unknowns here. A matrix is a multiplication matrix, V is a residual matrix here, all the residuals are there, and observations y1 to yn. I am writing L here. This is very easy to form. I can form A matrix easily, I can form L matrix easily, I can form V matrix easily, and X also. Fine. There are standard solution of this form, and phi equal to, that is nothing but V1 square plus V2 square plus Vn square, if you remember, because we have written summation Vi square I equal to 1 to n, or we also write it like this, y equal to I equal to 1 to n, here yi minus yi hat square, or I am just writing all the possible forms to avoid any confusion, yi minus mxi minus c whole square, right. So, we have already discussed in previous slides. This is nothing but Vi, so Vi square here. Now, I can write the same thing phi in the form of matrix capital V t into V, which is nothing but V1, V2, V3 up to Vn, and it is not V1, V2, Vn. So, if I multiply this thing, I will get same thing here, V1 square plus V2 square plus Vn square. And now, using the same principle of least square what we learned in the basic surveying, I can write what we have written this way, and we find out equations, and then we solve it. Here in the matrix form, I can write the solution X, which is nothing but m and c is given by AT A inverse AT L. And what is AT? This is A matrix, x1 1, x2 1, xn 1. It is n by 2 matrix here. AT will be transpose of A. L matrix is y1, y2, yn. So, if I multiply, I will get the 2 by n into n by 2, and then here again AT, which is nothing but 2 by n, and L matrix, which is n by 1 here. Here, if you remember the size. Now, if you multiply these two matrices, you will get 2 by 2 matrix. If you multiply these two matrices, you will get 2 by 1 matrix, and then if you multiply these two matrices, you will get 2 by 1 matrix, and which is nothing but size of x, right. So, we are very sure by dimensional analysis of matrices that we are going to get one column having two values. So, that is the idea here. If you have the data x1, y1, x2, y2, and so on up to xn, yn, you can formulate matrix A very easily, you can formulate matrix L very easily, and then you can write a solution just by multiplying and taking inverse. Nowadays, commercial IDEs or the free IDEs, IDEs means interactive development environment like Python, which is free. These inverse matrix multiplication are freely available, or rather they are inbuilt modules. So, now you can use those IDEs to find out solution of the problem. Okay, so that is the idea of the least square solution using matrix method, and this process is called the adjustments computation here. Okay, so let us go ahead and try to do few more examples. Let us fit a second order curve where I observe data xi, yi, I equals to 1 to n. Okay. Now, we introduced some error vi to the real data such that it becomes yi hat. So, again I can write here vi equals to axi square plus bxi plus c minus yi. So, if for n number of data, I can write here v1 equals to ax1 square plus bx1 plus c minus y1, v2 equals to ax2 square plus bx2 plus c minus y2, and for the nth data, I can write axn square plus bxn plus c minus yn. I hope you agree with this, and using this I am writing the matrix form V1, V2, Vn equals to x1 square, x1 1, x2 square, x2 1, and xn square, xn 1, and then here can write three variables a, b, c. They are unknowns. Now, here I can write y1, y2, yn. So, again this is V matrix, this is A matrix, this is matrix of unknowns, I call it X, and this is matrix L. So, I write the solution X equals to AT A inverse AT L. Again, let us look into the dimensions. A is nothing but, I can say, n into 3 matrix, here 3 into 1 matrix, here n into 1 matrix, and here V is n into 1 matrix. So, you try to find out whether the X matrix is 3 into 1 or not. You will get it. We have done two examples, and you can now formulate any problem. So, let us try to find mathematically what we have done in a generic terms, and now I will introduce few terms. In this slide, y is dependent variable. Because y is dependent on the x. The moment I'm giving the input value x by some function fx, I'm getting y value. Y is equal to mx plus c in case of linear example or the line fitting example. Okay, x is independent variable. Which is x here, or y is function of x. I always introduced error in the dependent variable y. That means y plus v, we wrote like this. We assume that x is independent variable, so it is without error. In fact, nothing comes without error if we measure in the field, but still we assume in this method that input variable or independent variable is without error, and dependent variable has some error. Now we have one more term called parameters, which is unknown. What are the unknowns here? These are my unknowns, what I call here x, this matrix, all three are unknowns. So now we are very clear on terminologies, limitations and assumptions here. Okay, let us go ahead. This method where I express explicitly y in terms of x is called observation equation method. Remember, I have taken two examples. The first example is y is equal to mx plus c, and another one was y is equal to ax square plus bx plus c. So this is dependent variable y, x is independent variable, and a, b, c are parameters. So I write it iv, and this is my dv, dependent variable, and we always introduced error in the dependent variable. Here I have a dependent variable explicitly given in the form of independent variable like this, or maybe like this. We also call this method as method of indirect observation or method of adjustment of indirect observations, because y is indirect observation and I am trying to adjust that y. How do I write mathematically? I write L, which is dependent variable, is function of some parameter x. This is an ideal relationship like y is equal to mx plus c, or ideal function. But the moment I have some error, I introduce an error here, v plus lb equal to, and this v plus lb I call adjusted value of the observation. That means if I add some v value to the lb observation, I will get the adjusted value, which means that is going to follow ideal mathematical relationship. Okay, so I write this as if LA equals to Fx finally. From here again I can write that v is equal to nothing but Fx minus Lb. I also explain the Fx equal to Ax. That means there is a matrix which is multiplying to x parameters, and I am getting some Fx. That's the idea here. And if you remember, okay, let me do like this. If you remember A matrix and X matrix, X was, let us say, unknown A, B, C, and if I write A matrix as, let us see like this, x1 square, x1 1, x2 square, x1 1, xn square, xn 1, and if I multiply with the X matrix like this, Ax, then it will be A, B, C. So this is the meaning here, I am writing it this way. So there I give the solution x equals to At A inverse At Lb, right. So I need to reduce in this form. The moment I bring this form here, I can write straight away the solution of unknowns. Okay, what about the quality of unknowns? Remember, we use the error propagation in order to find out the quality of any variable. Sigma xx, okay, I am not deriving the derivation here. I can straight away write the solution here, and that is given as AT A inverse. That is the quality, and nothing but in case of linear example, sigma xx is sigma m square sigma c square sigma mc here. That is the quality or the covariance of the m and c. Remember, the quality of m will be sigma m or the precision of m. Well, so before going into the quality aspects and all this thing, let us take few more examples which are pretty simple to understand. Okay, let me take the basic example of mean. We always say the mean is equal to most probable value. Let us prove this thing. So let us see that you have measured a variable x and you write the values like this, x1 plus v1, you will get the true value x, fine. Now you take another option x2, you add residual v2, you will get true value, and so on. Let us say you get xn plus vn, you will get true value x. Even I can use lower alphabets also to write, but meaning is same. Okay, so you are measuring basically the length, and you are measuring L1, L2 or x1, x2 and so on. Now I can write V matrix this way, V1, V2, Vn equals to, here I can write x, x, x n times minus I can write x1, x2, xn, fine. I hope I am just transferring the things from here to here, left to right and right to left. Okay. Here I can write this X matrix as 1, 1, 1 n times into unknown x minus x1, x2, x3 and let us say xn, same thing. And here again V1, V2, Vn. Now this is V matrix, this is A matrix, this is the X matrix which is unknown single value, and this is L matrix. So I have this form V equal to Ax minus L. I can find out x given by At A inverse At L. Okay, very simple. Now let us put the value of A and everything. It is very simple to put. At will be transpose of A, so A 1, 1, 1, 1 like this. Again A matrix 1, 1, 1 this way. Okay, the whole inverse I will take. Again the ATL, AT is nothing but 1, 1, 1, and L matrix is nothing but, I can write here L matrix as x1, x2, xn, right. If I multiply these two matrices, I will get one value here, 1 square plus 1 square plus 1 square and inverse of the whole matrix. Then if I multiply these two matrices here, I will get x1 plus x2 plus xn. Remember, this is 1 by n matrix, this is n by 1 matrix. Similarly, here it is 1 by n matrix and it is n by 1 matrix. So you will get 1 cross 1 here of this size of the matrix is 1 cross 1, and here also you get 1 cross 1. If you add 1 square n times, you will get n inverse, and here summation x1 plus x2 plus xn, and I can write it x1 plus x2 plus xn divided by n is nothing but the mean of all observations, right. Now I have proved it using adjustment computation principle that mean is the most probable value, because if you calculate now the VTV, right, which is nothing but sigma Vi square, right, that is not equal to 0. In case of true value or the population mean, it should be equal to 0, but in case of sample mean, it is never equal to 0. And hence we say that we have find out the best possible value from the given observation, but it is not equal to true value, and so we call it is a most probable value which has maximum probability of occurrence. So that's the concept of MPV, and now we have proven it, that why mean should be taken as MPV, not any other value. We have done the least square solution of a given data here. Okay, what if you have some weights? What about you should get the weighted average? Let us say that data is coming with different means. That means the x1 has some weight w1, x2, w2, and x3 is coming from w3 weight, and so on, xn coming with wn weight. Okay, so you should get the answer x equal to w1, x1, w2, x2, wn, x1 divided by w1 plus w2 plus w3 up to wn. I would like to modify solution. When we write x equal to ATA inverse ATL here, so if we consider the weight, then let us see there is a weight matrix P. So I write ATPA inverse ATPL. So what is weight matrix here? So in this case, we have assumed that weight matrix is identity matrix, or 1, 1, 1, 1, and all are zeros here, diagonal matrix. When we consider different weights, then what will be the weight matrix here? W1, W2, Wn. And since observations are coming from field and they are independent and there is no covariance variance between that time, so only the variance of the x1 is deciding W1. So I write P matrix like this. Again, develop V matrix. V matrix will be same. That means x1, if you add some value V1, you will get the true value. If you take x2, if you add V2, you will get the true value, and so on. So in the nth observation, if you add some residual Vn, you will get the true value, right? So now you can construct V matrix V1, V2, Vn in the form of A matrix, which is nothing but 1, 1, 1, 1 to 1 here, x here, and minus, let us see, x1, x2, xn. Now you will consider the P matrix here also and here also. So check whether you get this answer or not. You should get it. Do it yourself, take a homework. Let us take a multivariate example. So what is the meaning of multivariate? So far we have taken single output variable. Let us see that I have an image here and I want to georeference or refer this image to a map. Map is slightly, we can say, bigger one. So what I do in case of map, I observe capital X and capital Y, and in case of image, I observe small x and small y. So I know the pixel number, or maybe I can find out x and y. So let us see, these are the points I observe in the image. Let us say n number of points. That means it is small xi, yi. And here in the maps, I have some points like this, same corresponding one-to-one connection. Let us say I have marked 7 points here, mark 7 points here. So let's, this is 7 points, and here I can say, let's say this is capital Xi, yi. So if I say this is capital X1, y1, I have corresponding small x1, y1 here in the image. That's the meaning here. That means I have one-to-one correspondence between the points. Now I want to do some transformation between the image and map so that I can refer the image on map, or I can do the georeferencing of the image. So what do? I write these two equations. That means xi equal to axi plus b yi plus c is one equation, and yi I explained as plus e yi plus f. So there are two such equations, or rather it is a multivariate. In input we have xi yi, and output I have map coordinates capital X capital Y. So let us assume that if I introduce the error xii plus vxi, I'll get axi plus byi plus c. Okay. So because I am transforming my image into the map, so I am writing this equation. So let us see y. If I introduce yi here, I will get d xi plus e yi plus f. So if I write for n number of points, I can write here such equations. Let us see x1 plus vx1 equals to ax1 plus by1 plus c, y1 plus vy1 equals to here dx1 plus ey1 plus f, and so on. I can write for n number of points xn plus v xn equal to a xn plus b yn plus c, yn plus vyn equals to d xn plus yn plus f. So how can I write the V matrix and all this thing? So here I write Vx1, Vy1, Vx2, Vy2 and so on. So I can write Vxn, Vyn here. Then I am transferring this on the right hand side. So I can write here, let us see this x1, y1, 1 here, okay. Then I am writing here 0, 0, 0. Here I am writing A, B, C, D, E, F minus x1, y1, x2, y2, xn, yn, like this. I can fill these values like x1, y1, 0, here x2, y2, 1, 0, 0, 0. Here I can write here x2, y2, 1, and here 0, 0, 0. Similarly 0, 0, 0. Similarly if I write here xn, yn, 1, 0, 0, 0, 0, 0, 0, xn, yn, 1. This is V matrix, this is A matrix, this is X matrix unknown, and this is L matrix. So now I can write X is equal to AT A inverse AT L. So I will get X as A, B, C, D, E, F transpose. There is no space, so I am writing as a transpose. You will get a column matrix here. So now we have seen multivariate example or multi-response example also. That means we are getting more than one response if you give the input variable. So this is the idea here. At this stage, we need to understand that the observation equation method can be used when function or the output variable or the dependent variable is given explicitly in terms of independent variable or input variable, right? And we will also talk about the quality of the parameters. She said here sigma xx, which is nothing but ATA inverse. Moreover, I would like to say here, we know sigma LB, the quality of observation here. So, what is the meaning? We are talking about the quality of yi measurements. We write it here. So, sigma 1 square, sigma 2 square, sigma n square, all these are 0. Remember, using this only we have constructed our weight matrix P. Okay. So, now what about the quality of the adjusted values? That means, if I find out the quality of the residual sigma VV, I write a relationship which can be proven, sigma LB minus sigma LA. So, what is the meaning here? The quality of given or observed values are sigma LB, which is inferior than the quality of the adjusted values of the same variable. So, I am trying to adjust the variable y, and I can say here confidently that y is the variable which I am trying to adjust. So, after adjustment, whatever quality it has here, it is superior to the quality of observation, because sigma VV definitely will have variance terms, and that will be positive. And I can say that in order to make this matrix positive, I need to have this matrix higher values than this matrix. And I can say that the error in the LA, that is adjusted values, will be less compared to the what I observe, sigma LB. That is the meaning here. Then how can we construct the P matrix using the sigma values of the observation? Remember, these sigma values are for the y1, y2 and yn, because x we assume that there is no error in the x. Let us see, we know that weight of observation, which is given by, let us say, Wi of any observation, is proportional to 1 upon sigma I square, right? And I know sigma LB, it is nothing but sigma 1 square, sigma 2 square and sigma n square here, because they are all coming from the field observation. So, I say that they are uncorrelated, and in case of y is equal to mx plus c, this is LB, because if I adjust this value by V, I will get the adjusted value of A. For sigma 1 square is the for variance of y1, sigma 2 square is the variance of y2, and sigma n square is variance of ynth, because we do not have any estimate of this. Now, how to assume? There are three ways. First, if I am using some instrument, I know what could be probable error there. So, suppose total station, I know the specification of total station. I can also assume these values with my experience, or if you do not have experience, so even you can assume it vaguely, no problem, but you should try to develop some experience there. So, it can be arbitrary because it is assumed value, although it should have some logic to assume. It can be arbitrary also, since it is an assumption. Okay, now let us see that you have assumed, or based on your experience or based on specification, you have estimated these values by some way, and we call it sigma LB. There is a little problem. If I use this logic to find out the weight matrix P, which is nothing but here W1, W2 and Wn, all zeros here. First of all, if I take 1 upon sigma square equal to W, there will be problem of the units, which is a minor problem. Let us say someone observing in centimeter, someone is observing in meter. So, I will have different units of the sigma I square, and accordingly weights will be affected. But that is a minor problem that can be handled numerically. But there is a major problem, and the major problem is, first of all, I do not know the value here. So, what can I do? But I know one information. I know that whether this observation y2 is superior to y1, or yn was superior to some other observation. Based on that, I can say, yes, I am confident about y1 that it is at least 50% better than y2. So I can say the weight of y1 is 1.5 while weight of y2 is 1, because I am feeling that y1 observation is 50% better or something like this. I know how many times something is better than other. So I have some idea about weights. I use this information to construct the weight matrix, but I also use the variance information. So how to do it? Let us say weight is given by k upon sigma square, which is nothing but this principle only. Now I write Wi equal to k by sigma square. Let us see some observation having one weight. So if I write here 1 equal to k times, and if I write sigma 0 square, which is also I am assuming, so I can say sigma 0 square equal to k, and if I replace this value over here, I can write Wi equal to sigma 0 square upon sigma I square. So here, first of all, two things are happening. I call this sigma 0 as variance of unit weight, or I also call it the reference variance. So reference variance of unit weight, or I call it the reference variance. Again, I am assuming this value because I am taking the ratios of sigma 0 and sigma I. So it is alleviating two problems to me. First, no problem with the units. Secondly, even if I do not know sigma 0, sigma I, still I can construct the weight by assuming sigma 0 and sigma I. So that way I will have the weight matrix in terms of some numerical numbers which are ratios, and so I will have this W1 which is independent of unit, but they are still representing the quality or the mutual quality of all the observations together. So this is the way we construct the weight matrix. And now in the formula ATPA inverse ATPL, you can use the P as weight matrix. Okay, after doing this thing, we will stop here. In the next lecture, we will look into the problem of nonlinear cases. Thank you for having patience, and try to practice what we have done and try to do your homework.